The authors introduce PoCL-R, a groundbreaking computing runtime that enables scalable multi-access edge computing with server-side scalability. By leveraging the open heterogeneous computing standard OpenCL, PoCL-R allows compute tasks to be executed on multiple servers in a scalable manner. This novel runtime gracefully handles intermittent user equipment (UE), connection loss and IP address changes, minimizing network-induced latency through peer-to-peer data transfer and command signaling between remote devices. Synthetic benchmarks show command latency of only 60 microseconds on top of network round-trip latency. PoCL-R can further accelerate inter-server data transfers by utilizing RDMA, achieving an additional 60% speedup compared to TCP-based solutions. In a smartphone-based augmented reality rendering case study, offloading AR rendering from a smartphone results in up to 19x improvements to frame rate and 17x improvements to local energy consumption. Scalability to multiple GPU servers is demonstrated in a computational fluid dynamics simulation, achieving roughly 80% efficiency comparable to an MPI port of the same simulation. PoCL-R addresses key challenges in multi-access edge computing (MEC), including the need for a vendor-neutral way to access heterogeneous compute accelerators efficiently and seamlessly. With its API based solely on OpenCL, PoCL-R enables accelerator code portability across various UE local and MEC-side devices. The runtime is designed for use by application developers directly or as a backend for higher-level APIs like SYCL or CUDA (HIP). Notable features of PoCL-R include peer-to-peer communication and synchronization between compute nodes, support for high-performance and low-latency demands, and graceful handling of connection loss and restoration on unreliable networks. As the first distributed OpenCL runtime integrated into a widely used open-source OpenCL implementation framework, PoCL-R is both usable and extensible for anyone freely. This article builds upon an early version of PoCL-R presented in a conference publication, tackling more challenging MEC use cases and presenting additional usage scenarios. The authors introduce their work on Remote Direct Memory Access (RDMA), support for server-side buffer migrations, achieving up to 60% speedups compared to simple TCP socket communication. They focus on delivering a device-portable yet general-purpose solution for multi-access edge cloud (MEC) compute execution. The paper highlights the challenges of MEC offloading, including latency, packet loss, and network congestion. Recent developments in wireless networking, such as 5G and Wi-Fi 6, are discussed as improvements. The authors emphasize the need for MEC solutions that utilize heterogeneous compute resources locally and in encountered MEC servers, ensuring software portability. They introduce OpenCL, a cross-vendor standard for heterogeneous compute, which divides the application logic into host and device-side programs. The authors review previous work on offloading and distributing compute workloads, noting most projects have faded into obscurity. Their proposed runtime targets high-performance compute clusters and real-time applications, focusing on latency and client portability. The work is compared to SNUCL, which targets HPC clusters and prioritizes throughput. PoCL-R is an OpenCL-based remote driver that facilitates a client-server architecture for distributed computing tasks, particularly suited for low-power user equipment (UE) devices connected via wireless links to powerful compute clusters. It supports multiple remote servers and diverse compute devices such as GPUs and FPGAs, with a focus on minimal end-to-end latency, server-side scalability, and seamless recovery mechanisms in case of connection drops. The PoCL-R runtime uses the Portable Computing Language, PoCL, as its client-side implementation, which is an open-source implementation of the OpenCL API. This allows for direct use of the OpenCL API for maximum efficiency or as middleware for improved productivity APIs. The remote driver interfaces with remote OpenCL-supported devices through distributed communication, making them appear identical to local devices. PoCL-R's key benefit lies in its cross-vendor portability, unlike projects like RCUDA, which is limited due to being based on the proprietary CUDA API. Other related projects, such as SNUCL and RemoteCL, have limitations in terms of scalability, hardware support, and generalizability. The server side of PoCL-R consists of a daemon that runs on the remote server, providing a peer-to-peer communication model to avoid round trips back to the client during synchronization or data transfers between remote devices. This setup enables efficient distributed execution of diverse tasks across multiple devices, as depicted in Figure 1. In summary, PoCL-R offers a flexible and scalable solution for distributed computing tasks, leveraging the OpenCL API and supporting various hardware platforms. It is designed to cater to the needs of low-power devices requiring high-performance computing capabilities, while ensuring minimal latency and robustness against connection issues. PoCL-R is a novel remote OpenCL computation framework designed to enhance the efficiency and scalability of mobile devices by leveraging external compute servers for resource-intensive computations. The system operates through a client-server architecture, where the client dispatches commands to one or more remote servers, each equipped with an OpenCL driver. These servers manage the execution of commands and dispatch them to their respective OpenCL devices. In the event of a connection loss, PoCL-R gracefully handles this by marking devices as unavailable, attempting to reconnect, and resuming command submissions once reconnected. It also maintains a backup of the last few commands sent and resends them before any other commands upon reconnection. Higher software layers can utilize device availability information to manually fall back to performing computations locally, either at full precision with increased power consumption or at reduced quality with simpler algorithms. The PoCL-R daemon is structured around network sockets for client and peer connections, with each socket having a reader and writer thread. The reader thread dispatches commands to the underlying OpenCL runtime, stores associated OpenCL events in a queue, and signals the corresponding writer thread. The server writer thread iterates through events in the queue and writes results to the socket representing the host connection when an event is complete. To enhance latency and scalability, PoCL-R employs peer-to-peer communication, allowing devices on the same server to migrate OpenCL buffers directly between them, and supports a number of shorter paths when available. It also introduces a 16-byte session ID to facilitate reliable reconnecting without retransmitting unchanged data. The server keeps track of IDs it has handed out and uses them to attach incoming connections to the correct contexts. This enables seamless reconnection and minimizes data retransmission. PoCL-R, a heterogeneous computing framework, optimizes buffer transfers in multi-access edge computing environments by leveraging high-speed internal networks for direct peer-to-peer transfers between servers. This approach eliminates the need to transfer large buffers across the slowest link in the system, reducing network round trips and bandwidth usage. The framework employs decentralized command scheduling, ensuring the task graph remains intact for runtime optimizations. PoCL-R's decentralized architecture consists of servers directly connected to each other, enabling buffer migrations and command completion notifications without client round trips. To address dynamic buffer content size issues, PoCL-R introduces an OpenCL extension for specifying actual used buffer sizes, reducing wasted bandwidth and memory. Additionally, it utilizes RDMA-based server-side buffer transfers to minimize buffer transfer overhead. The research paper discusses the control flow of transferring a buffer between servers via TCP sockets and RDMA. In TCP communication, commands are prefixed with a size field to avoid bandwidth waste, and commands requiring additional data have their sizes included in the command metadata. This process involves multiple system calls for large transfers, leading to inefficiencies. In contrast, RDMA communication operates on a message-based model, handling message sizes internally and allowing for chained messages. This reduces the number of system calls and improves efficiency. The paper highlights the issue of varying command struct sizes in TCP communication, which can lead to unnecessary data transmission. To address this, PoCL-R utilizes a shadow, or scratch, buffer that is registered for both incoming and outgoing RDMA transfers. Upon receiving a transfer completion notification, the shadow buffer's contents are uploaded to the right OpenCL buffer internally. Similarly, on the sending side, buffer contents are copied into the shadow buffer when a migration command is received before issuing the RDMA transfer request. The paper suggests that a shadow copy of each buffer is not needed if the server's native OpenCL runtime supports allocating SVM buffers. These buffers can be associated with proper addresses in the virtual address space of the application process and can thus be registered directly as RDMA memory regions. This mode of operation can be enabled with a compiled time option and is expected to yield noticeable improvements to performance and memory usage. The benchmarks presented in the paper used the shadow buffer solution due to limited SVM support. The paper concludes by noting that as SVM and related technologies gain wider support, expanding the cross-node DMA to support direct transfers between GPU memories could be an interesting future direction. APIs like NVIDIA GPU Direct can be used for registering GPU memory directly as RDMA regions. The authors of the research paper evaluate PoCL-R, a distributed OpenCL runtime, focusing on its latency and scalability. To measure command overhead, they create a synthetic benchmark that dispatches an empty kernel, measuring the duration of the invocation. The results show that OpenCL commands take around 60 microseconds more than the network latency, which is considered a good result. This overhead remains constant even when running the client application on the same machine as the server daemon, indicating that it is solely due to the runtime. In comparison with SNUCL, a similar framework that focuses on data center use and total throughput scalability, PoCL-R outperforms it. They benchmark a simple pass-through kernel that copies a single integer from an input buffer to an output buffer. The results show that PoCL-R commands take only 1/6 of the time compared to SNUCL. However, when compared to calling the NVIDIA driver directly, PoCL-R still takes twice as long, indicating room for improvement. The authors also investigate data migration overhead, which is reported to be a bottleneck in some SNUCL benchmarks. PoCL-R supports migrating buffers directly between servers in a peer-to-peer fashion, which is expected to reduce overhead. Although the results of this benchmark are not presented on this page, they will be discussed in subsequent sections. The performance evaluation of the proposed system focuses on the migration of buffers between servers and scalability under non-trivial workloads. A synthetic benchmark measures the duration of a migration of a 4-byte buffer between two devices using different connectivity methods. The results indicate a significant reduction in average migration time when using a 40 gigabits per second direct link compared to a 100 megabits per second wired Ethernet connection. This reduction is attributed to the dedicated direct link without network equipment or interference. The paper also explores the performance gain achieved by utilizing RDMA instead of TCP socket communication for buffer migration. Using RDMA results in a speedup of almost 30% for small buffers, which improves to around 65% for larger buffers due to reduced overhead. The system scalability is assessed using a distributed matrix multiplication test, demonstrating satisfactory performance and scalability under non-trivial workloads. The authors present a benchmark for distributed matrix multiplication using 1 to 16 remote devices, each with 4 GPUs, to evaluate the scalability of their proposed system, PoCL-R. The benchmark involves multiplying two 8192 by 8192 matrices, with each device computing a roughly equal number of rows of the result matrix. While the computation is embarrassingly parallel, collecting the intermediate results from each device into a single buffer is non-trivial. The authors compare their results to those reported by SNUCL authors, who also used matrix multiplication as a benchmark. The benchmark results, shown in Figure 12, demonstrate a logarithmic performance increase as more GPUs are added, reaching a speedup of slightly less than 6x when using all 16 GPUs. This is comparable to the results reported by SNUCL authors when using their proposed MPI collective communication extensions. Notably, PoCL-R does not exhibit the performance regression seen in SNUCL when using more than 8 devices. In contrast, naive distributed matrix multiplication using RDMA, shown in Figure 13, provides no meaningful speedup for small work sizes and even results in a net negative performance for large numbers of servers due to the overhead of registering RDMA memory regions and informing peers of the keys for said regions. The authors also present results for real-world application case studies using PoCL-R, including an augmented reality application that enhances rendering quality by offloading computation to a mobile edge computing (MEC) server using PoCL-R. This application involves real-time point cloud augmented reality rendering, where a point cloud is received as a video-based point cloud compression (VPCC) stream encoded with HEVC, decompressed with a hardware HEVC decoder, and reconstructed using OpenCL shaders. The points are then sorted by distance from the viewer and rendered using alpha blending to produce a visually pleasing result. In the realm of augmented reality (AR) applications, enhancing performance and reducing energy consumption on mobile devices is a significant challenge. To address this issue, researchers have developed a system that offloads heavy computation tasks to a high-powered compute server. This approach allows the smartphone to focus on other tasks while maintaining AR functionality. The system operates by having the smartphone decode and reconstruct points of a point cloud, then sorting these points by distance to an arbitrary point using the compute server. This division of labor enables the mobile device to conserve resources and improve overall efficiency. The paper also highlights the use of OpenCL for device classification and the PoCL-R daemon for exposing video decoding hardware as an OpenCL device. These tools play a crucial role in optimizing the system's performance and energy efficiency. The results of this approach are substantial, showing a significant speedup and reduction in energy consumption when compared to performing all operations solely on the mobile device. This innovative method has the potential to revolutionize AR applications, making them more accessible and sustainable for users. In this study, the scalability of the FluidX3D tool, a computational fluid dynamics simulator utilizing the lattice-Boltzmann method, is assessed in real-world scenarios. The performance of the NVIDIA driver is compared to PoCL-R, a multi-node distribution framework that eliminates the need for application code modifications. The test setup consists of a local desktop PC, 3 remote servers equipped with 100 gigabits per second fiber optic interfaces and NVIDIA RTX A6000 GPUs, and a 100 gigabits per second switch. Benchmarks were conducted in various configurations, including TCP, RDMA, and native modes, with varying numbers of server nodes. Results show that PoCL-R's performance scales almost linearly with the number of server nodes, similar to the NVIDIA driver's scaling with local GPUs. However, a slight overhead in GPU utilization is observed when using PoCL-R, primarily attributed to network speed limitations. The localhost benchmark reveals that this overhead is mainly due to network speed, as running the simulation with PoCL-R on the same machine yields throughput comparable to using the NVIDIA driver directly. The use of RDMA does not significantly improve performance, as the boundary buffers are small enough to fit within the kernel side send and receive buffers of the TCP stack. The study highlights the inefficiency of the NVIDIA driver's device-to-device copy approach, which circulates data through main memory, and suggests that direct RDMA transfers from GPU memory to GPU memory could enhance performance scaling. Furthermore, the initialization phase is bottlenecked by the desktop's gigabit connection, while the client traffic remains steady at 7 kibibytes per second per used GPU, and peer-to-peer traffic between servers reaches 231 megabytes per second. Approximately 2 gigabits per second, RX, TX per server, totaling around 12 gigabits per second. The authors present the performance results of their proposed distributed OpenCL-based heterogeneous computing runtime, PoCL-R, in figures 16 and 17. Figure 16 shows the FluidX3D performance in millions of lattice updates per second, demonstrating a significant increase in performance with the use of PoCL-R. This improvement is also reflected in the GPU utilization, as illustrated in figure 17. Where an 80% utilization rate is achieved with 1 GPU per server node. The authors emphasize the importance of peer-to-peer transfers in achieving this performance, highlighting the impracticality of routing 12 gigabits per second of traffic through the client application. The results suggest that PoCL-R is a viable alternative to MPI as a distribution layer for some applications, given its comparable performance scaling. The authors further demonstrate the suitability of PoCL-R for real-time MEC offloading, achieving up to 19x better frame rates at around 5.7% of the energy consumption in an AR point cloud renderer running on a smartphone. Additionally, the performance scalability of PoCL-R is demonstrated through a computational fluid dynamics simulation, showing a multi-node efficiency of around 80%. The authors believe that PoCL-R can serve as a compute layer for heterogeneous distributed edge offloading cases with high performance and low latency requirements. This page provides an extensive compilation of research papers, each focusing on various aspects of advanced technologies and their implications for future development. The list includes studies that delve into the intricacies of artificial intelligence, blockchain technology, quantum computing, and biotechnology. In the realm of artificial intelligence, several papers explore novel algorithms and methodologies designed to enhance machine learning capabilities. These include deep learning techniques, reinforcement learning strategies, and the integration of AI with other technologies such as robotics and the Internet of Things, IoT. Blockchain technology is also a significant focus, with research highlighting its potential applications beyond cryptocurrencies. Papers discuss blockchain's role in supply chain management, secure data storage, and smart contracts. Furthermore, they examine the challenges and limitations associated with implementing blockchain technology on a large scale. Quantum computing is another area of interest, as researchers investigate the potential for quantum computers to solve complex problems that are currently intractable for classical computers. This section covers quantum algorithms, quantum cryptography, and the development of quantum hardware. Lastly, the compilation touches upon biotechnology, encompassing genetic engineering, CRISPR technology, and synthetic biology. These papers explore the ethical considerations and potential societal impacts of these emerging technologies, as well as their potential benefits in fields such as medicine and agriculture. Overall, this comprehensive list offers a broad overview of cutting-edge technologies and their potential to shape the future. It serves as a valuable resource for researchers, policymakers, and stakeholders seeking to understand the complexities and implications of these technologies.